There is something most people never think about. The moment you focus on a single word on this page, your brain is not seeing what your eyes show it. It is seeing a heavily edited reconstruction, assembled from incomplete data, filled in with predictions and rendered in real time with no perceptible delay. The human eye does not function like a camera. It functions more like a rough sketch artist working alongside a master painter. One captures the outline, the other invents the rest. Understanding the true anatomy of the human eye means understanding not just a structure, but an argument the body makes with light itself. Every waking second of your life, the eye sits in a bony socket called the orbit, a protective cup of bone that cradles it on all sides except the front. The average adult human eye measures just under an inch in diameter, roughly the size of a large marble, and weighs about 1/4 of an ounce. Despite its modest size, it contains more than 2 million working parts. It is one of the most metabolically active structures in the entire body, demanding a continuous supply of oxygen and nutrients even during sleep. That demand is not trivial. The eye has its own internal circulation system, its own immune-privileged status, and a set of specialized tissue types found nowhere else in the human body. Before we go inside, it is worth asking why the eye evolved at all. And the answer is stranger than it first appears. Light receptors have existed in living organisms for hundreds of millions of years. Simple, single-celled creatures use photosensitive proteins to detect the difference between light and dark. But the step from a patch of light-sensitive cells to a fully directional, focusing optical organ like the human eye is one of the most discussed transitions in evolutionary biology. Evidence suggests it happened not once but multiple times across different lineages, which says something profound. The pressure to see was so constant, so unrelenting, that evolution kept arriving at similar solutions independently. The human eye is not a miracle. It is a convergent answer to an ancient question. Now let us go inside. The outermost surface of the eye is the conjunctiva, a thin, transparent mucous membrane that covers the white of the eye and lines the inside of the eyelids. It produces a thin layer of mucin, a component of the tear film that keeps the surface lubricated. Beneath it, the tough white layer of the eyeball is the sclera. Dense and fibrous, made of interwoven collagen strands, the sclera gives the eye its structural rigidity. It is the reason the eye maintains its shape under normal conditions. At the front, the sclera transitions seamlessly into the cornea. And this is where everything changes. The cornea is the eye's primary lens. That is worth pausing on, because most people credit the lens, the structure visible in diagrams, as the main focusing element. But the cornea, not the lens, performs the majority of the eye's optical work, responsible for roughly 2/3 of its total refractive power. It curves gently over the front of the eye and bends incoming light before it reaches anything else. It does this without blood vessels. The cornea is one of the few tissues in the human body that is entirely avascular. There is not a single blood vessel running through it. Blood vessels, with their opaque walls, would scatter light and destroy clarity. Instead, oxygen diffuses directly into the cornea from the tear film and from the aqueous humor inside the eye. The cornea is alive, metabolically active, and completely transparent, a biological feat that required its constituent collagen fibrils to be arranged with near crystalline uniformity. If those fibrils become disorganized, as happens in scarring or disease, transparency is lost. The cornea clouds over, and vision dims. Behind the cornea is the anterior chamber, a small fluid-filled space. This fluid, the aqueous humor, is produced continuously by the ciliary body, a ring of tissue sitting just behind the iris, and drains through a specialized meshwork near the angle where the iris meets the cornea. The aqueous humor is not simply water. It carries nutrients to the avascular tissues of the front of the eye and maintains intraocular pressure, the internal pressure that keeps the eye firm and its surfaces precisely curved. Healthy intraocular pressure sits between about 10 and 21 millimeters of mercury. When the drainage system becomes partially blocked and the pressure climbs beyond that range, the optic nerve at the back of the eye begins to suffer. That condition is glaucoma, and it can destroy vision silently with no pain before the patient is aware anything is wrong. The iris is the colored ring that makes every human eye recognizably unique. It is a thin, muscular diaphragm, and its primary job is to control the size of the pupil, the opening at its center through which light enters. In bright light, the sphincter pupillae muscle contracts, constricting the pupil to as small as about 1/10 of an inch in diameter. In dim light, the dilator pupillae muscle flattens the iris, opening the pupil to as wide as about 1/3 of an inch. This adjustment happens within a fraction of a second and is controlled entirely by the autonomic nervous system. You cannot consciously override it. The iris also receives signals from the brain related to emotional state, cognitive load, and arousal. Pupils dilate when the brain is processing something cognitively demanding. They dilate in response to fear. They dilate when looking at a face you find attractive. The eye does not just look. It communicates inward states involuntarily. Just behind the iris sits the lens, a biconvex, transparent structure suspended by fibers called zonules, which are attached to the ciliary muscle surrounding it. The lens performs a function the cornea cannot. It changes shape. When the ciliary muscle contracts, it releases tension on the zonules, allowing the lens to become more spherical. When the muscle relaxes, the zonules pull taut and flatten the lens. This dynamic adjustment is called accommodation, and it is what allows the eye to shift focus from something inches away to something 100 yards in the distance. The lens at age 10 is remarkably elastic, able to change its curvature with great speed and range. By middle age, that elasticity has declined considerably. The lens grows stiffer throughout life, and eventually the ciliary muscle can no longer deform it sufficiently to focus on close objects. This is presbyopia, the near-universal age-related loss of close focusing ability. It is not disease. It is the mechanical consequence of a lifetime of use. The lens also yellows slightly with age, filtering out progressively more blue light. This shifts color perception imperceptibly at first, then meaningfully. Studies of painters in late life who developed cataracts, a clouding of the lens, show shifts in the palette and texture of their work. The color information reaching the retina changes as the lens changes. Behind the lens, filling the bulk of the eyeball, is the vitreous humor, a clear gel-like substance composed largely of water and a mesh of collagen fibers and hyaluronic acid. It maintains the eye's spherical shape and transmits light to the retina at the back. The vitreous is largely stable, but with age its gel begins to liquefy in patches and pockets of liquid form within it. Collagen fibers clump together, casting shadows on the retina. These shadows are what most people know as floaters, those translucent specks or filaments that drift across the visual field when looking at a blank sky or a white wall. For most people, they are harmless. In some cases, however, the vitreous pulls away from the retina, a condition called posterior vitreous detachment. And if the force is sufficient, it can create a retinal tear. A retinal tear, if unaddressed, can progress to a retinal detachment, one of the few ophthalmic emergencies that can cause permanent blindness within days. Now we reach the retina, and this is where the anatomy becomes, in the truest sense, extraordinary. The retina is not simply a screen, it is an outgrowth of the brain itself. During fetal development, it forms as a cup-shaped protrusion of the developing diensphalon, the same region of the brain that gives rise to structures like the thalamus. By the time the eye is fully formed, the retina is a thin sheet of neural tissue lining the inside of the posterior eyeball, approximately the size of a postage stamp, no thicker than a sheet of paper. It contains roughly 120 million rod photoreceptors and about 6 to 7 million cone photoreceptors. It also contains bipolar cells, ganglion cells, horizontal cells, and amacrine cells. 5 distinct classes of neurons organized into layers, performing initial image processing before signals leave the eye entirely. Rods are responsible for vision in low light. They are extraordinarily sensitive, capable of responding to a single photon of light under ideal conditions. They are distributed across most of the retinal surface, but are absent from the very center. They do not distinguish color. They report simply on the presence or absence of light. This is why, in dim conditions, colors seem to wash out, and why objects at night are easier to see when you look slightly to the side of them rather than directly at them. You're shifting the image from the rod-free center to the rod-rich periphery. Cones are responsible for color vision and fine detail. They come in 3 varieties, each tuned to a different range of the light spectrum, roughly corresponding to red, green, and blue wavelengths. The brain compares the activity of these 3 cone types to generate the full range of color perception. Some individuals carry a gene variant producing a 4th type of cone, slightly shifted in its spectral sensitivity relative to one of the standard 3. These individuals, almost all of them women due to the X-linked nature of the relevant genes, may be capable of distinguishing shades of color that appear identical to people with the normal 3-cone complement. Research continues to explore the true extent of this capacity and how the brain integrates the additional channel. The highest density of cones is at the fovea, a small pit at the center of the retina directly behind the lens. In an area no larger than the head of a pin, the fovea packs in more than 150,000 cone cells per square millimeter, the highest density of any visual receptor in the eye. This is where you see with the sharpest acuity. When you look directly at something, you are placing its image onto the fovea. Everything else in your visual field is processed with progressively lower resolution as you move toward the periphery. The reason you do not perceive the world as a blurry ring around a sharp center is that your eyes move constantly. Microsaccades, small fixation movements, and sweeping shifts, resampling different regions and allowing the brain to construct the illusion of uniform detail. At a point about 15 degrees to the nasal side of the fovea, the optic nerve leaves the eye. There are no photoreceptors at this point. Light falling on this region is not detected. This is the blind spot, and every human being has one in each eye. You do not perceive it because the brain fills it in using information from the surrounding retina and from the other eye. If you close one eye and locate the blind spot precisely, you will find that objects disappear into it. The brain has been quietly papering over this gap your entire life without announcing it. Where the retina passes the baton to the brain, the complexity only increases. The optic nerve carries approximately 1.2 million nerve fibers, the combined output of all the ganglion cells in the retina, to the brain. The 2 optic nerves from each eye meet at the optic chasm, a crossing point just below the hypothalamus, where fibers from the nasal half of each retina cross to the opposite side of the brain, while fibers from the temporal half remain on the same side. This partial crossing means that visual information from the left visual field of both eyes is processed by the right hemisphere of the brain, and vice versa. The optic radiation then carries signals to the primary visual cortex at the back of the head in the occipital lobe, where the first stages of higher visual processing occur. But the journey does not end there. Information fans out into dozens of distinct processing streams, each analyzing a different aspect of the visual scene. Motion, color, depth, object identity, spatial location. The visual system uses roughly 30% of the cerebral cortex. Vision is not a peripheral function. It is the primary organizing project of the human brain. The system supporting all of this is remarkably well supplied. The retina is nourished by 2 systems, the retinal blood vessels, which supply the inner layers, and the choroid, a dense vascular layer lying just outside the retina, which supplies the outer layers, including the photoreceptors themselves. The choroid is one of the most vascularized tissues in the body, delivering more blood per unit weight than almost any other organ. This is not incidental. Photoreceptors are among the most metabolically demanding cells in the body, and they consume oxygen and glucose at extraordinary rates. Each rod and cone is constantly cycling through a phototransduction cascade, a rapid sequence of molecular events triggered by light, and must continuously replenish its supply of photosensitive pigment. The outer segments of photoreceptors, the tip of each rod and cone, are renewed every 10 to 12 days. Old disc membranes shed at the tips are consumed by the retinal pigment epithelium, a single layer of cells just outside the retina that performs this daily cleanup. If the retinal pigment epithelium begins to fail, as happens in age-related macular degeneration, the leading cause of blindness in older adults in the developed world, the accumulation of cellular debris and the loss of photoreceptor support leads to progressive destruction of central vision. There is no surgical fix to simply replace the retinal pigment epithelium. Research continues to explore cell-based therapies, gene therapy approaches, and prosthetic devices that can bypass damaged photoreceptors entirely. Some experimental retinal implants convert light to electrical signals delivered directly to the remaining healthy nerve cells in the retina, creating a crude form of functional vision. The images are low resolution and pixelated, but the principle has been demonstrated. The eye and the brain can accept artificial electrical input and construct something recognizable as perception. What the anatomy of the human eye ultimately reveals is a system whose sophistication exceeds any optical instrument we have ever built. No camera achieves the dynamic range of the human visual system, capable of adjusting from detecting individual photons on a moonless night to functioning in full afternoon sunlight, a range spanning more than 1 billion to 1 in light intensity. No display renders the same color space perceived by a healthy human retina. No lens system in any device combines the cornea's fixed power, the lens's active accommodation, and the neural processing of the retina into a seamless, self-calibrating unit that runs without maintenance for decades. And yet the system has limits we have only recently begun to articulate. The blind spot, the reliance on prediction, the way color perception shifts with age and lens density, the vulnerability of the retina to detachment, degeneration, and pressure. These are not flaws in a failed design. They are the marks of a structure shaped by millions of years of selective pressure that could optimize only within constraints. The constraint of fitting a complex optical instrument into a bony socket less than 2 inches across, maintaining it without replacement parts, growing it from a handful of embryonic cells in the first weeks of life, and sustaining it with nutrients carried in blood vessels too large and too opaque to touch its optically critical surfaces. The human eye is not a window, it is an argument. Assembled in the dark of the womb, refined across evolutionary time, running silently every moment you are awake, about what it means to encounter the world through light. Look at anything right now, anything at all, and you are witnessing the conclusion of that argument as it is delivered, continuously, to a brain that already decided what it would see before the image arrived. If there is one thing this journey through the human eye reveals, it is that vision is not a passive act. It is an active construction, a continuous negotiation between light, biology, and the brain's predictions about reality. Every image you have ever seen has been filtered, interpreted, and, in many ways, invented before it reached your awareness. And yet, despite its limits, this system allows you to experience depth, color, motion, and meaning with a precision no machine has fully replicated. So the next time you open your eyes, remember, you're not just seeing the world. You are participating in one of the most sophisticated processes evolution has ever produced. If you want to keep exploring how the human body truly works beneath the surface, subscribe to the channel, because what you've seen today is only a small part of a much deeper system waiting to be understood.